we have just seen that going from the view that there are absolute beings with absolute properties to the view that there are only relative beings with relative properties can help us a lot to resolve, or at least to dispel, some quantum paradoxes. We started with the Schrödinger's cat paradox, but now we'll see also how to dispel another paradox of quantum physics, which is the famous paradox of the wave-particle duality. How is it possible that a single being is simultaneously a wave widely spread in space and a little corpuscle, very located here and there, okay? How is it possible? This idea of the wave-particle duality was imagined by Einstein in 1905. Because, you know, at that time, in 1905, Einstein knew the conception of light and electromagnetic waves that came from the past, namely essentially from Jung, Fresnel, Maxwell, and Hertz. According to these physicists, light is a wave. Light has the nature of a wave. But then Einstein showed that certain effects that were observed in the laboratories, for instance, the famous photoelectric effect, in which you create an electric current if you light a certain electrode with photons, well, with light, in fact. Then, in order to explain that, Einstein said the only way to explain this effect is to accept that light is not made only of waves, but it has also the nature of corpuscles, particles. So he was a little bit upset, because he said there are some effects that are observed on light that can only be explained if we accept that light is a wave, and some other effects that can only be explained if we accept that light is made of particles that we now call photons. So he stayed with this puzzle. Einstein stayed with this puzzle. In 1909, for instance, he said, okay, how can I imagine this combination of waves and particles? Maybe I can put the two together. And he said, I tend to imagine these points, the points, namely the particles of light, as if they were surrounded by a field of forces having the nature of plane waves. So he imagined the duality of waves and particles as if a sort of, little dot, a little particle, was surfing on an ocean of waves. Then in 1910, Einstein was even more puzzled with this idea. He felt that there was something wrong with it. And he asked, can we reconcile the quanta of energy with the Huygens principle? Huygens principle is just the principle of waves. Full stop. And he added, this seems impossible to reconcile corpuscles and waves. But God seems to have found the trick. It's very funny, you know. So what Einstein meant is that humanly it's very difficult to understand. But maybe God, who created the world, had understood it. But then Einstein was even more skeptical 1 year later, in 1911. He said this conception, namely the idea that there are particles that are connected with waves, is provisional, since it doesn't seem to be reconcilable with the experimental consequences of the wave theory. Namely, there is something wrong with this idea, because the picture of particles is contradicted by wave-like effects, and the wave picture of light is contradicted by particle-like effects. So Einstein just said, okay, probably this is provisional. I don't want to go deeper in that. But strangely, in this very same conference of 1911, there was a certain Maurice de Broglie, brother of Louis de Broglie, a famous French physicist, who attended the conference and heard Einstein's talk. And then Louis de Broglie decided to apply the same idea of a duality between wave and particles to matter, not only light. And by this duality of matter and, this duality of particle and waves, he managed to explain why electrons going around the nucleus in the atom jump from one quantized state to another quantized state instead of having continuous motion. So you know that at that time, Bohr posited what he called the rules of quantization, namely that an electron can only adopt discrete, discontinuous orbits. But then, with his waves, de Broglie explained that. So it was wonderful. I put some equations for you to see, but it's not really to be taken seriously. The idea is just that waves were enough, according to de Broglie, to explain the famous Bohr's rules of quantization. And Einstein, when he saw that, said, wow, he made a wonderful discovery. This de Broglie is a genius. He has lifted a corner of a great veil, said Einstein about de Broglie. Now, what can we say about this dual nature of wave and particle? Can we say that there is a single being that is intrinsically endowed with wave-like properties and particle-like properties? As Einstein said, this idea sounds absurd, because one property is to be in a single place of space, and the other property, namely being a wave, means being extended everywhere. So the two properties are deeply contradictory. And if you look very carefully at the phenomena, you see that this association is not compulsory. The association of waves and corpuscles in a single being is not necessary. Why? For instance, you see this diffraction effect on top of the slide. And this diffraction effect is usually produced by a wave. When you have a wave, you have a diffraction effect when the wave goes through a hole. But should we say that conversely, each time you see such diffraction picture, then it is necessarily caused by a wave? By no means. Logically, this consequence doesn't follow. Why? Because you can find explanations, alternative explanations of this diffraction pattern without postulating waves. So waves are not the only possible explanation of this diffraction pattern, and maybe when you see the diffraction pattern, there is no wave at all. The same for these tracks in a bubble chamber. They look like they depict the trajectory of a particle, but in fact they depict the alignment of a multiplicity of bubbles, of discrete events. And therefore, you can account for this alignment of bubbles without postulating that there is a particle endowed with a trajectory and going through the chamber. You can, for instance, have a a wave-like explanation of the so-called particle-like effects. So you see that clearly you have no proof that things that are either waves or particles. Maybe it's not the case that they are both particles and waves, but maybe it's the case that they are neither particles nor waves. And there is a theorem by a French physicist and philosopher of physics, Paulette Détouche-Février, that shows that a theory, a probabilistic theory, applying to phenomena that are relative to mutually exclusive contexts, predicts wave-like distribution of the phenomena. Namely, here you see that waves are just an appearance, and that the reason for this appearance is that phenomena, the phenomena to which quantum physics tries to account for, these phenomena are relative to a certain experimental arrangement. So, what is more deep than wave-like effects is that the fact that they express the relativity of phenomena which are accounted for by quantum physics. Relativity is crucial here. So, I told you that probably we have nothing like neither waves nor particles. What we have, what we observe, is dots. Dots on the screen, or clicks on a counter, nothing more. And if certain devices are used, such as an interferometer, for instance, or a diffraction slit, if certain devices are used, these dots distribute as if there were a wave. But it's only as if there were a wave, not there is a wave, you see. The same for corpuscles. The alignments arise in certain experimental contexts. The alignments of the dots arise in certain experimental contexts and not in others. So here again, you cannot say there is a particle, there is a trajectory, but relative to a certain experimental context, it looks like there is a particle-like behavior. Relative to another experimental context, you have a wave-like behavior. And very interestingly, you may have any combination of the two. Namely, relative to certain mixed contexts, experimental contexts, you have also a mixture of wave-like and particular behavior. That means that, I insist on that, waves do not exist, particles do not exist, but relative to certain experimental contexts, you have particle-like effects. Relative to other experimental contexts, you have wave-like effects. So relativity is the key, and here again we come back to this really powerful way to understand the so-called paradoxes of quantum mechanics, is to remove own being and to adopt relative being instead.